Hi there, welcome to this video where we continue taking a look at Richard Dedekind's essay, The Nature and Meaning of Numbers. So this video continues on from where the previous video finished off. So in the previous video, on this particular essay, I managed to get up to theorem 58 in chapter 4. So chapter 4 is quite a long chapter, so I've split it into two videos. I got up to theorem 58 in the last video, which is about 2/3 of the way through the chapter. So we're going to continue in this video from theorem 59. So as usual, this video is unscripted, so you're gonna have to bear with me if I do need to think from time to time about what I want to say and about what's written. I do have some notes, brief notes that I may need to refer to at some point, because we're going to be looking at theorem 63 from this chapter, which Dedekind himself doesn't actually prove. He leaves it as something for the reader to do. So I will be presenting my own proof of theorem 63. So just to make sure that I get it right, I've got some notes that I might need to briefly refer to. I'm going to be reading through the contents of the chapter and giving my interpretations and providing a bit of explanation, just giving a bit of commentary, really, as to what I think Dedekind is getting at, what I think is going on. As usual, though, whatever I say in this video is my interpretation. It's not necessarily definitive. It will help if you've got some familiarity with the contents of Dedekind's essay up to this point. Otherwise, you might there might be some terminology that I use that you're not necessarily familiar with. Of course, I've made the last 4 videos that I've made on this, going through some of the contents. Feel free to use those if they're helpful. But at the very least, I would recommend that you read through the contents of Dedekind's essay, whether in English translation or German. Obviously doesn't make any difference, as long as you've got some familiarity with the contents. So let's get started then. So let me find the right page. Where are we? So we're starting with theorem 59. Oh, it's already highlighted. Okay. It's maybe from the last video, I don't know. Okay, so theorem of complete induction. So this is kind of a generalization of the usual proof by induction, let's say, that you may be familiar with if you've got some familiarity with certain techniques, certain proof techniques that are commonly used in mathematics. So the basic idea behind proof by induction, as it's usually introduced, is that if a particular proposition Pn is true when n equals 0, and it's also true, we assume that it's true when n equals k, and this implies that it's true when n equals k plus 1, then we can say that Pn is going to be true for all natural numbers. So this is kind of a generalization of that kind of idea. So there are a few things that I want to say about this, but I'm going to leave those for after I've gone through the proof of this particular theorem. So let's get started then. So in order to show that the chain A0 is part of the system sigma, be this latter part of S or not, it is sufficient to show that rho A is a part of sigma and lowercase sigma, that the transform of every common element of A0 and sigma is likewise element of uppercase sigma. Okay, so a few sigmas floating around here. The system is uppercase sigma. The point, the condition or whatever, is lowercase sigma. So I'll try to remember to use uppercase sigma and lowercase sigma whenever appropriate. Okay, we're on to the next page. Okay, so proof. If rho is true, so rho is the condition, the assumption that the system A is a part of the system uppercase sigma, then by 45, there's a lot of backwards and forwards. to-ing and fro-ing with some of the references. It's well worth doing, by the way. It's kind of frustrating from time to time as you're reading through. There's these references all the time, but to familiarize yourself with the theorems and things like that, it is worth going back and checking the reference 45 here, for example. Just making sure that you're fully aware what that theorem says, rather than just saying, "Oh yeah, Dedekind's, it's cited theorem 45. I'll just accept it." I mean, there's nothing wrong with that, but really to familiarize yourself with the particular theorems and that Dedekind presents in this work. Sometimes that repetition of actually going back and constantly referring to these can help you to familiarize yourself with the layout of the work and start to have kind of a mental map of where particular theorems are in the work. Not necessarily essential to do, but I find it really helpful to do. So theorem 45 is that A is a part of its the chain of A. Okay, so A naught, remember that's the chain of A. And by definition 44, A will always be a part of its chain. Okay, so we're using that. So if rho is true, then by 45, the community G equals the community of A naught and uppercase sigma certainly exists. So why is that? Because A is a part of A naught and A is a part of sigma. So this is by theorem 45. This is by rho. So therefore, remember, we don't have empty systems here. So A is effectively assumed to be a non-empty system. Okay, so therefore there must be some common parts of A naught and uppercase sigma. Okay, so that means that the community must exist. Okay, and by 18, A is a part of G. Okay, so I don't remember off the top of my head what 18 says. So let's have a look. So 18 is that every common part of A, B, C is part of the community of A, B, C. So, okay, so every common part of A, B, C, the community, and by 18, A is part. Right, okay, so why is that? Because A is a part of A naught, A is a part of sigma. So yeah, it follows from 18, the conditions of 18 directly, that A must be a part of the community of A naught and sigma. Since besides by 17, G is a part of A naught. So let's have a look at what 17 says, because I don't remember off the top of my head. A thing G is, oh, okay, so, oh, yeah, it's just by definition, right? 17 is the definition of community, right? G is a common part of A naught and sigma by definition. Okay, so G is a part of A naught. Okay, so G is a part of A naught, and that's by definition. Straight from definition 17. Then G is also part of our system S. Because A naught is by... A is a part of the system S. Okay, it doesn't say this as part of the statements of the theorem, but if we go back to a previous comment, where was it? I think 21, definition 21. We agree that, so right at the end of definition 21, we agree that small and capital italics without accent shall always signify elements and parts of this system S. So A is a part of the system S. Okay, this is a capital italic letter, so we assume that it's part of the system S. And by 44, if A is any part of S, we will denote by A0 the community of all those chains of which A is a part. So all those chains within the system S. Okay, so what was I up to? So G is also, so since A0 is a part of S and G is a part of A0, then also is G a part of S. I think I said that right. Which by phi is transformed in itself, and at once by 55 we have also, so phi is a transformation of S in itself, and at once by 55 we also have, right, okay, so since A0 is a chain, then the transfer, and G is a part of the chain A0, then the transform of G will also be a part of the chain of A0. Yeah, so that's theorem 55. So G is a part of A0, therefore G primed, the transform of G, is a part of A0. If then sigma is likewise true, i.e. G primed is a part of sigma, so what does sigma say? That the transform of every common element of A0 and sigma is likewise element of sigma. So G is a common part of A0 and sigma, and G primed is the transform of all of the elements in that common part. So we need to show if then sigma is likewise, oh no, so by assumption sigma, lowercase sigma, G primed is a part of sigma. Okay, so G primed is a part of sigma, and this is by point lowercase sigma. Then must G primed as common part of the systems A0 and sigma by 18 be part of their community. Okay, so G primed is as a common part of the systems. Right, okay, so we've got G primed is a part of A0, G primed is a part of sigma, so G primed is a common part of A0 and sigma, and therefore G primed must be part of G. Yeah, so that's from 18. G is a chain. Right, so that's the definition of chain. Okay, so go back to definition 37. That shows that G is a chain. And since, as noted above, A is a part of G, so that's here, then by 47 is also, right, so what we've shown here, when we say that A is part of G, now we've shown that G is a chain, we can see that A is a part of a chain, and therefore A0 is part of G. And therefore, by combination with the preceding result being this one, that G is a part of A0, now we have that A0 is part of G, then we can use whichever, is it theorem 5? Theorem 5 will say that G is equal to A0. Hence by 17, also A0 is part of sigma. So where do we get that from? A0 is... So G is a common part of A0 and sigma. Aha, yeah, right. So, going right back to the top here. Of course, G is a common part of A0 and sigma. So we have that G is part of sigma. Hence by 17 also. So G is right. Okay. Yeah. Of course. Because G is equal to a naught. That's what we've proved, right? G is equal to a naught. So a naught is a part of sigma, which is what we needed to prove. That a naught is a part of our system, uppercase sigma. So really, it's not a particularly difficult proof. It's just figuring out, just satisfying yourself that all of these relations of part to, you know, this is a part of that, and so on and so forth, that they all just convincing yourself that they are right. Okay, so that's the proof of that. So just a few comments on this. So I think, let me clear a little bit of space actually, because I think I'm going to need a bit of space. The way that induction is often kind of presented can sometimes, in my opinion, can be a little bit misleading or inconvenient. The way that we might have a tendency to think about it. I'm not saying that this particular way that I'm going to describe in a second forces itself upon us, and that everybody will necessarily think about induction in the way that I'm about to describe. But I think there is a certain the way that induction is often initially presented to us can kind of give us the impression that it's somehow something that kind of gradually emerges. So we've got a particular proposition, Pn. We prove it for n equals 0. And then we assume, so I've already said this previously in this video, but it's relevant again now. We assume it for n equals k, and we show that this implies it's true for n equals k plus 1, and therefore Pn holds for all natural numbers. Okay, so sometimes we might start with n equals 1, actually. I've just chosen n equals 0. It actually doesn't make too much difference as long as we've got a start point. Okay, so it could be n equals 0, it could be n equals 1. In some cases, it could be n equals 2 or 3 or whatever, as long as you've got a definite start point. So if you don't like me using n equals 0 as the start point, just rewrite it with n equals 1. So this is often compared to kind of a like a domino effect. Okay, you knock the first domino over, the next domino falls over, and the next one, the next one, the next one. But you kind of get this idea that it's kind of a gradual thing, and this can be kind of misleading in some ways. It can be, in my opinion, better to think about this as something that happens all in one go. Okay, so it's difficult for me to explain really what I'm kind of getting at, but this transformation that's involved here, okay, phi, it's not something that we gradually apply to A. So it's in this case we've got kind of a generalization. We're starting with a set, a system A. And we might have a tendency to think about it as kind of repeated application of phi to the elements of A. So we apply phi to the elements of A, and we potentially get an enlarged system. Okay, with the transforms. Not only do we have A, but we've got all of the transforms of all of the elements of A. But then we apply phi again, and we get a further enlarged system. And we apply phi again, and we keep getting this gradually greater and greater and greater system. And this, to me, is not necessarily the best way of thinking about it. So because this necessarily, in a way, it kind of relies on, we don't necessarily want to be thinking about phi being applied a finite number of times, or a countably infinite number of times, or an uncountably infinite number of times, or something like this, because we don't have these concepts available to us at this stage. We haven't defined, it's not till the next chapter that we define finite and infinite, so we can't limit ourselves in this way to kind of repeated applications of phi. Everything has to happen all in one go, so to speak. So the way that I tend to think about it is that all of these systems involved here, A naught, and sigma, they already exist. In a sense, they already exist in their entirety. That it's not something that the system A naught, the chain of A, is not something that we kind of gradually build up. It's something that already exists. It's a system in itself. It's kind of a part of the system S, but it has a certain relation to the system A. Okay, the relation that it has to the system A is described in definition 44. Definition 44. Okay, so I try to, in certain circumstances, I try to avoid thinking about the transforms that are involved here. I try to avoid thinking about them as kind of dynamic things. Okay, literally like they're taking an element from a system to an element in another system. I'm not saying that this is a wrong way to think about things, or it's a bad way, but what I would, rather than thinking about, let's say we've got our systems S and T, for example, and we've got a transform. So we've got S here, and we've got S primed over here. Rather than thinking about it, this transform as literally taking the element S and taking it to the element S primed, I think about it as kind of a static relation. In certain contexts, I'll think about it as a static relation between S and S primed. Now, it does help in some contexts to think about functions as more dynamic sort of things, literally taking something and transforming that thing, that object, into something else. But there's a kind of time aspect there, maybe, that might enter into our considerations, which we don't really want to be introducing here. So me personally, in this context, I'm thinking about these transformations, phi and psi, as we'll see further down the line, as static relations. Okay, so S and S primed already exist, and it's just there's a certain relation. So to each element in S, so we've got S, we've got A, we've got all of these elements here, and this transform, which is between the systems S and T, and we've got elements over here in the system T. We've got fixed static relations between the different elements of S and the different elements of T, as opposed to this kind of dynamic relation, or dynamic transform, which takes the elements of S and somehow transforms them with an almost kind of time aspect to it, transforms the element S into the element S primed. Okay, that's just, again, this video is just really me expressing some of my interpretations and the way that I think about Dedekind's work and what I find useful. I'm not saying that it's right. It might not even make sense what I'm saying, but these are just some of the things that go through my mind as I'm reading this work, and some of the things that I take into consideration. Okay, so let's have a look at theorem. It's not really a theorem, actually. It's more of a remark. So remark 60. So the preceding theorem, as will be shown later, forms the scientific basis for the form of demonstration by the name of complete induction. I can't remember where this is actually. I can't remember which part it's in, but it's certainly later on anyway. The inference from n to n plus 1. It can also be stated in the following manner. In order to show that all elements of the chain A0 possess a certain property, see, I'm not great. Is that an E? Somebody correct me. I read it as an E. I'm not particularly familiar with this font, to be honest with you. So somebody correct me. It looks like an E to me, but I'm showing my ignorance, aren't I? Although it's a theorem S, dealing with an undetermined thing n actually holds good for all elements n of the chain A0. It is sufficient to show rho that all elements A of the system A, uppercase A, possess the property E, or that S holds for all A's, and lowercase sigma, that to the transform n primed of every such element n of A0 possessing the property E belongs the same property E, or that the theorem S assumes it holds for an element n of A0 certainly must also hold for its transform n primed. Indeed, if we denote by uppercase sigma the system of all things possessing the property E, or for which the theorem S holds, the complete agreement of the present manner of stating the theorem with that employed in 59 is immediately obvious. Okay, so on to theorem 61. The chain, which is the... I've got to get my terminology right now. This is the problem. I've been looking at all sorts of things over the last week, so I can get confused with my terminology. So compounded, right? So it's the system compounded out of A, B, C is equal to, so the is here is expressing equality, is equal to the system compounded out of the chains A0, B0, C0. So if we designate by M the former and K the latter system, so in other words, we've got M is equal to the system compounded of A, B, C, and so on, and K is the system compounded out of their chains, then by 42, K is a chain. So in other words, the system compounded out of chains, out of systems which are chains, is also a chain, if I remember rightly. 42. Yeah, system M compounded simply, whatever that means, out of chains A, B, C is a chain. Okay. So we know that A0, B0, C0 are chains by definition, so therefore K is a chain. So since then by 45, 45 says that A is a part of its own chain. So by 45 we know that A is a part of A0, and we also know that A0 is a part of K. So I can't remember which that's from. That's from earlier on. So each of the systems A, B, C is part of one of the systems A0, and therefore by 12. Okay, so A0 is a part of K. So since A0, we can apply the same to B. So B is a part of B0. B0 is a part of K. We can do this for all of the systems. So in other words, A0, B0, C0 are all part of K, and therefore the system compounded out of these is also part of K, part of one of the systems, and therefore by 12M. Sorry, no, something's not right here. I've made a mistake somewhere. Since then, by 45, each of the systems A, B, C is part of one of the systems A0, B0, C0, and therefore by 12. Let me just check what 12 says. If each of the systems PQ is part of one of the systems A, B, C, So the system compounded. Oh, right. Okay. So no, I was thinking of the wrong thing. Right. So each of, right. So yeah, A, B, right. Yeah. So A is a part of K. B is a part of K. So that's applying theorem 5 or maybe theorem 7. Right, transitivity. Theorem 7. Theorem 7 applied to this gives that A is a part of K. Transitivity applied to this, B is a part of K. So therefore, the system, by 12, the system compounded out of A, B, C, and so on and so forth. In other words, M is a part of K. And then because K is a chain, the chain of M is also a part of K. So that's one of the things that we needed to prove. On the other hand, since by 9, each of the systems A, B, C is part of M, okay, and hence by 45 and 7, also part of the chain M0. So M0 is the chain of M. So 45, what does that say? Oh yeah, and 7, 47. On the other hand, by 9, each of the systems A, B, C is part of M. So A is a part of M, B is a part of M. So by 45, also part of the chain M0. Oh, of course, yeah. Oh, right. By 45, I was thinking about the wrong thing. It's 45 being applied to M. M is a part of M0. So then by 7, we get that applying 7, again, transitivity to this, we get that, running out of space here, A is a part of M0, transitivity applied to the other one, we get B is a part of M0. So therefore, each of the systems A0, right, okay, so because M0 is a chain by definition, then by 47, A0 is a part of M0, B0 is a part of M0, and so on and so forth. So therefore, the system compounded of A0, B0, and so on is a part of M0. In other words, K. So we conclude from this that from all of these, sorry, that K, the system compounded of A0, B0, and so on, is a part of the system M0. So K is a part of M0, M0 is a part of K. It follows by theorem 5 that M0 is equal to K. K is equal to M0. Whence by combination with the preceding result follows the theorem to be proved, right? Because the theorem to be proved was the chain of, so we weren't wanting to prove that M is equal to K. We were wanting to prove that the chain of M is equal to K. Okay, so on to theorem 62. So the chain of the community of ABC is part of the community of A0, B0, C0. So whereas in the previous, in theorem 61, we had equality between the chain of the system compounded of A, B, C is equal to the system compounded of the chains of A, B, and C. Here, we don't necessarily have equality. There might be conditions under which we can guarantee equality, but we don't get into that here. Let's have a let me clear a bit of space. So I'd be really grateful, by the way, if you would consider subscribing to the channel, hitting the like button, and leaving a nice comment in the comments section. If there's anything that's unclear that I say in these videos, please let me know. If you've got any questions about anything, feel free to leave your comments in the comments section, any questions that you've got, or contact me directly, and I'll be happy to help wherever I can. Okay, so if we designate by G the former and by K the latter system, so we've got G is the community of A, B, C, and so on, and K is equal to the community of A0, B0, C0. We want to prove that G0, the chain of the community of A, B, and C, is a part of K. That's what we want to prove. Okay, we want to prove. We haven't proved that yet, obviously. We can't assume that. That's what we want to prove. So it's not that we're wanting to show that G is a part of K, and it's very important, I think, to acknowledge that the chain of the community of how can I say this? If we start with G, which is the community of A, B, C. I mean, this is effectively what we're trying to prove here. There's some kind of relation between the two. Just because we find the chain of G, it doesn't mean that we can pass this symbol here over to each of the A, B, C. Okay, so it doesn't automatically follow. Therefore, it might be tempting to do things like this, but it doesn't automatically follow that we have equality here. And in fact, what we're wanting to prove is that G0 is only a part of this. Okay, so let's see how this goes. K is a chain because it's the community of systems which are themselves chains. So what was that, 43? The community G of chains A, B, C is a chain. So we know that A0, B0, C0 are by definition chains, so therefore K is a chain. Each of the systems by 40. Since then, each of the systems A0 by 45 is whole of one of the systems A, B, C. Okay, so we know that A is a part of A0, B is a part of B0, C is a part of C0. A reversal of terminology here. So rather than reading this as A is a part of A0, we can say A0 is a whole of A. So Dedekind talks about this right at the beginning. I actually don't, I find it a bit clumsy, the terminology whole. So, but that's the terminology that he uses. So that's the terminology that we're going to use here. So if you look in definition 3, he talks about this. So A0 is a whole of A, B0 is a whole of B, C0 is a whole of C, and therefore by 20, where's 20? If each of the systems ABC is whole of one of the systems PQ, then the community of PQ and so on is part of the community of ABC. So in other words, the community of A naught, B naught, C naught, and so on is part of the community of A, B, C. Okay. The chain is the chain of that is part of that. Have I got that the right way around? It's by 20. So yeah, G is a part of K. And by 47, since K is a chain, then the chain of G will also be part of K. Okay, oh, we're on to the next page, aren't we? Okay, so that finishes the proof of for theorem 62. So now on to theorem 63, which I'm going to have to refer briefly to my notes throughout the proof of this. So I'm going to be going through the proof of this. If there's any errors in it, which I hope there aren't any errors, then please feel free to let me know. Okay, so theorem, if K primed is a part of L, so that's the transform of K. So remember, K primed is the transform of K under some transformation. It is part of L, which is part of K, and therefore K is a chain, since by transitivity we can see that K primed is a part of K. L is also a chain. If the same is okay, so we need to let's prove that first, and then we'll have a look at the rest. So if we've got K primed is a part of L is a part of K, then we know from theorem 22. So in particular, focusing on this, L is a part of K, then L prime, the transform of L will be part of the transform of K. So that means that we've got L primed, the transform of L is a part of the transform of K, which is a part of L. Okay, using this other condition here, this other inclusion, and therefore L is a chain. Okay, so that's the first bit done. If the same is proper part of K, so in other words, if L is a proper part of K, and I think this is L is a proper part of K, so then so what he goes on to say is L is a proper part of K, and U the system of all those elements of K which are not contained in L. Dedekind has this thing about the empty system. He wants to exclude it from consideration, and this works. This is right back at the beginning. Point 2. We intend here, for certain reasons, wholly to exclude the empty system which contains no elements at all. Okay, so I think that when he insists on L being a proper part of K, it's so that U, the system U, will not be such an empty system. So he doesn't deny the existence of an empty system as such. It's just he doesn't want to bother with it. Okay, so I think that's why we potentially one of the reasons why he insists on L being a proper part of K. To be perfectly honest with you, I've not gone through. I've not thought about it really. What if L is equal to K? I've not actually thought about it, so I don't know what happens in that case. So somebody let me know what happens in that case. So okay, we know that K is L is a chain. So U is the system of all those elements of K which are not contained in L. And if further the chain U naught is proper part of K, and V the system of all those elements of K which are not contained in U0, then is K equal to the system compounded of U0 and V, and L is equal to the system compounded of, I can't read that properly, the transform of U0 and V. Okay, and then that final bit, if finally L equals K prime, then V is a part of V prime. We'll leave that for, we'll deal with this first bit first. Okay, so this is where I'm going to have to refer to my notes. So by assumption then, U0 is a part of K. Okay, since U0 we're told is U is the system of all those elements of K which are not contained in L. So U is the system of all those elements of K. So we're thinking of U as a part of the system K, and therefore we're thinking about the chain of U as a part of K. Well, it would follow anyway, actually. Because if U is a part of K, then K is a chain. We're told that K is a chain. So it follows from 47 or something like that. Theorem 47. Where is it? Yeah. Theorem 47. It follows then that U0 is a part of K. So I think so. That's justified. And V is a part of K by definition. V is the system of all those elements of K which are not contained in U0. So V is a part of K. Then by 10, the system compounded of U0 and V is a part of K. So I'm looking at this here. I'm wanting to prove this K is equal to the system compounded of U0 and V. So I've got one of the inclusions here. So now I need to show that K is also a part of the system compounded of U0 and V. So let's say that K is an element, lowercase k, is an element of the system K. So then, because of the way that U0 and V are defined, either K is an element of U0, or K is an element of V. So therefore, since K must be in at least one of U0 or V, in fact, it can't be in both because by definition. But it still stands that K must be in at least one of U0 and V. Then by definition of the system compounded of U0 and V, K must be an element in the system compounded of U0 and V. But remember that K was any element of uppercase K, and therefore K is a part of the system compounded of U0 and V. So therefore, putting these two together, theorem 5 will say that K is equal to the system compounded of U0 and V. Okay, so we're done with the first one. Okay, so let's have a look. The next one's a bit more fiddly. I'm not saying by that these the proofs that I give here are necessarily the best proofs. They're just the ones that I didn't spend a great deal of time with this. So there might be better proofs out there. If anybody else wants to have a go at proving them, and let me know how you get on, and if you find a better proof, then I'd love to hear about it. Okay, so since U0 is a part of K, so we've already discussed that, then by 22, U naught primed is a part of K primed. K primed is a part of L. So by 7, theorem 7, U naught primed is part of L. And so we've also got that V is a part of L. So I'm going to justify that now. Let's suppose that V is not a part of L. So, okay, yeah. Let's say that there's an element V, lowercase v. Suppose V, let me rewrite that. We should be able to get a contradiction here. So suppose V is a part of uppercase V, then that means that, let me think about this. But V is not in L. But not in L. V would have to be a part of U. My notes are not very good here. Why would V have to be a part of U? Oh yeah, by definition, of course. Yeah, right. So if we think about it, right, maybe I should draw a diagram down here. So just a rough kind of visualization of this. We've got K, we've got L here, which is this bit, and then outside of L, we've got, now this is, don't take this too literally, okay? This is not literally how things are. This is a very overly simplified kind of visualization, but the point that I'm making is that if this element lowercase v is not in L, then it must be in U by definition, right? So U is this bit outside of L. By definition, U is the system of all those elements of K which are not in L, right? So, but not in L. So in that case, V, lowercase v, is a part of U. But then we know that U is a part of U naught. It's chained by definition. That's definition 44. So that means that V must be an element. And remember this symbol, this part symbol, it serves to say, we can use it to say that something is an element of a system, or this system is part of, this system of more than one element is part of another system. So V is an element in U naught. But that's a contradiction, right? V is an element in V, and V is an element in U naught is a contradiction, because U naught is by definition all of those. V is the system of all those elements of K which are not contained in U naught. So V can't be an element of V. Lowercase v can't be an element of V and U naught. Okay, so that means that if V is an element in V, then it can't be the case that it's not in L. So every element of V, of uppercase V, is in L, and therefore V is a part of L. Okay, so that justifies that. And oh, okay, so we've almost done what we needed to do. So that means that because we've got where was it? U naught primed is a part of L and V is a part of L, then that means that the system compounded of u naught primed and v is a part of L. So I don't know off the top of my head which that is. Back in chapter 1 somewhere, one of those propositions in there somewhere. Okay, so we've got one direction, so to speak. So this is what we wanted to prove here, that L is equal to the system compounded of u naught primed and v. So we've shown that the system compounded of u naught primed and v is part of L. We need to show the other way now, that L is a part of the system compounded of u naught and u naught primed and v. Okay, so back to my notes then. By 58, what's 58? Aha, okay, so 58. We've got then that u naught, the chain of u, is equal to the system compounded of u and u naught primed. Okay, so that's theorem 58. We also have that v is a part of L. So that's the system uppercase v. Should make that a bit clearer then. The system v is a part of L. Thus any element of L which is not an element of v is also an element of k, because all of this is taking place in k, which is also an element of, right, so any element of L which is not an element of v is an element of k which is not an element of v, and so must be an element of u naught by definition. Well, I'd say by definition, almost by v and u naught. So we've got a similar diagram to, if I just rename the parts of this, we've got, if we call this u naught, then this in the middle here is going to be v. Okay, so there's no elements that are in u naught and v simultaneously. In the same way that there are no elements that are simultaneously in u and L, but then there are no elements of k that are in neither u naught or v. Okay, so we could call these mutually exclusive or whatever, right? There's no overlap anyway. So such an element of L is either an element of u or u naught primed. So it must be an element of, right, okay, so such an element. So such an element of L, so we're choosing I'm choosing an element of L here. And so it must be an element, so it's in u naught. Aha, okay, right, yeah, because, so we choose an element of L. Then it's either in an element of L which is not an element of V. We've shown that it must be in u naught, and therefore it must be in at least, because u naught by 58 is equal to the system compounded of u and u naught primed, then L, this element that we choose, must be either in u or it must be in u naught primed. Okay, but u contains no elements of L. That's by definition of u. So must be an element of u naught primed. Okay, so the element of L that we've chosen, which is not an element of V, must be an element of u naught primed. So thus any element of L which is either an element of V or an element of u naught primed. Okay, so in other words, L is part of the system compounded of u naught primed and V. So again, putting this together with this, we get what we need, which is that L is equal to the system compounded of u naught primed and V. Okay, so I'll just go on to another clean page. Oh, what do we need to prove now? if L equals K primed, the transform of K, in other words, then V is a part of V primed. Okay, so L is equal to K primed, and that's an uppercase K, by the way, if there's any confusion. Then since K is equal to the system compounded of U0 and V, then by, I don't know which one, let me have a look. This will be in chapter 2, I would imagine. Oh. The K primed, the transform of K is equal to the system compounded of the transforms of U0 and V. The transform, right, so that's theorem 23. And therefore, since K primed is equal to L, we've got that L is equal to, therefore, the system compounded of U0 primed and V. Sorry, V primed, forgive me. But we've also shown, right, here, that L is equal to, also L is equal to the system compounded of U0 primed and V, right? So on the one hand, we've got L is the system compounded of U0 primed and V primed, and U0 primed and V on the other. And since U0 primed and V have no common element, then it follows that V must be a part of V primed. Okay, so it might be that when we go to V primed over here, there's more elements in V primed than there are in V. But V primed has to at least contain V. It has to. If it didn't, then there would be an element of L which is kind of missing here. We wouldn't have equality with L. We can view this as kind of minimal in a certain sense. There's no overlap between U0 primed and V. Okay, so we can't remove any elements from U0 primed or any elements of V without losing the equality here. So once we go over to this side, L equals the system composed of U0 primed and V primed, we can't have removed any elements from V. U0 primed is still the same. We can't have removed any elements from V. We can only have added elements. There might be no elements. It depends. V might be a chain, or whatever. But it follows that V must be a part of V primed in that case, and that's the last thing that we needed to prove there. So Dedekind says that the proof of this theorem, which as of the two preceding we shall make no use, may be left for the reader. So there we go. That's the my demonstration of that particular theorem. Okay, so any questions that you might have regarding anything in this video, again, please feel free to ask. I'm going to leave it there with this video. We're moving on next to chapter 5, the finite and the infinite, where we find Dedekind's attempt at characterizing the finite and the infinite, and we'll see. I've got a bit to say about that. So what I've said in previous videos is that I'm not really subjecting this to deep critical analysis or anything like that, but there are some interesting things that I want to say about Dedekind's particular the way that he tries to characterize the finite and the infinite. Give a bit of background into some of the issues that maybe arise from that, from his particular formulation. Okay, so I'm going to leave it there for this video. Please feel free to subscribe to the channel, hit the like button, don't forget to leave a comment in the comments section, and I will look forward to seeing you in the next video.